So thank you. So it's a pleasure to me being here today, and thank you for your interest in this topic, and especially in this topic in relation to the mass unstable and edge system and engineering. So I've been asked to provide an overview on what are the environmental issues and challenges around the energy systems and the different technologies. And I'm doing that before then my colleague Jean-Marie will then take over the presentation and explain you how those knowledge and those tools will be integrated into this MIS. I'd like to start with this graph, which seems a bit awkward, but it basically show you what's the current state on Earth in relation to the temperature. And that graph goes back to several millions of years. So we have a logarithmic scale. And you can see that in the last 10,000 years, 10 to 12,000 years, this period that is called Holocene, it's a period which is known by its extremely stable temperature. So, and this is where civilizations has grown. So, if we are here today and with this level of well-being and with all this knowledge, so civilization is on Earth because we've benefited from this stable temperature. And now, well, as you certainly know, we are up to phase out from this Holocene and entering into the Anthropocene. So, say it differently, so we're experiencing an increase of temperature. And why this increase of temperature? Well, we might relate that increase based on some facts which are science-based. On one hand, we increased our human activities fueled by different type of fossil energies, coal, oil, natural gas, nuclear, and lots of renewables. So you've seen after the Industrial Revolution that we have been an exponential increase in this energy demand fueled by fossils. And we've seen parallel to that exponential increase in greenhouse gas emissions. So this is a fact. And there is another fact which it seems that it's only recently known, but in reality, Arrhenius in the early 1900s and so on already made a hypothesis that by releasing more CO2 in the atmosphere, well, we might see an increase in temperature. We've seen more recently that some studies made by some oil industries were projecting already in the 80s an increase in temperature because of an increase of carbon dioxide in the air. And if you see in 2020, so they were pretty much projecting what you observe as per today. And more recently, the International Panel of Climate Change, well, scientifically defined that there is a relationship between the cumulative carbon dioxide emissions into the atmosphere and the surface air temperature change. And so you can see that we are exactly on a linear relationship. So we've seen that there is a temperature increase because of greenhouse gas emissions, and these greenhouse gas emissions are related to the fact that we are using fossil fuels to sustain human activities. So the solutions then, as per today, is to move out, shift out from fossil and move into a new era, I would say, or say it differently, we need to defossilize our energy system. And to do so, well, we need to rely on clean energy, renewables, that might be wind, solar, hydropower. In the European nomenclature, we also have nuclear as a green or clean energy. And also think about storage solutions beyond just hydropower dams. We might also think about synthetic gas and so on and so on. So, and now I had a colleague that told me a few years ago, well, you know, Manuele, today we cannot afford to do the wrong decision, to take the wrong decision. So, and how to take the good decision or to avoid the wrong decisions is to use the appropriate tools. And one of these appropriate tools is life cycle assessment. And it's life cycle assessment is a way of looking at a technology, at a product or a service along the whole value chain. And by doing that, we realize that comparing fossil energies, for instance, here, it's a comparison of different technologies to produce 1 kilowatt hour of electricity. So we can see electricity produced by hard coal, natural gas, nuclear, concentrated solar power, photovoltaics or winds. We can observe that if you look how many energy we need to put into the system to produce the horizontal red lines, which is 1 kilowatt hour of energy out, we see that with fossils, we need much more energy in to get what we need as a final energy demand. And I'm still not speaking about useful energy demand. So it tells us that we have lots of inefficiencies in our system that we need to deal with. And if we move from fossil to renewables, we realize that we can take as much as this, much of this energy that we need out from the nature. So renewables are there for free, and we need to invest in infrastructure to harvest that energy. But still, it's not zero emissions. We need to invest in building this infrastructure. We need we need concrete, we need steel, we need aluminium, we need transportation, and so on. And because of that, well, also those renewable energies inherit some burdens on along the value chain. And this was for energy, but we could apply the same life cycle perspectives also to account for the carbon footprints. And in that case, on the horizontal axis, we have the same technologies. And by the way, this is a study which has been published by the United Nations Economic Commission for Europe in 2022. We can see that in terms of carbon intensity, technologies that use hard coals or natural gas, you can see as those are as high as 1,000 grams of greenhouse gases emissions per 1 kilowatt hour of electricity. And if we move to renewables, we can see that we are constantly and steadily below 100 grams per kilowatt hours, and even way below. Taking the example of hydro or wind, we are down as much as 10-20 grams of green CO2 equivalents per kilowatt hour of electricity produced. But there is a downside, and this is why we need holistic tools. I mentioned to you before that we need to build an infrastructure, and of course, moving from fossil to renewables, well, we need to build this infrastructure. So we need to build photovoltaics, we need to build hydro dams, we need to build nuclear power plants, we need to build windmills and so on. And to do so, well, we need materials. And this is similar graphs with another type of indicators, with another criteria, or with another type of lenses that we can compare the different technologies. And we see that renewables requires a bit more, up to 2 to 3 times more minerals than fossil to fulfill the same functions, meaning to produce 1 kilowatt hours or megawatt hours of electricity. So, so everything doesn't relies only on carbon, but if we are looking at environmental problems more broadly, we realize that we need to consider more criteria than carbon. And this is another graph that basically summarizes my previous ones, that tells you that moving from fossil to renewables, we basically will shift burdens from the operation phase to the infrastructure. So, and this is where we need to pay some attention to make the right investments, or to keep track of the right mitigation measures to minimize those burdens that we potentially could increase by developing this new infrastructure. And this is exactly what lifecycle assessment allows you to do. It's to understand a technology over the whole value chain, from the acquisition of resources to the production of those technologies, logistic operations, and ultimately the end of life, whether we recycle or we dispose all those technologies. And as I mentioned to you before, we make some pressure on the environment, meaning we are not only affecting the well-known problem about climate change, but we might also affect problem in resource depletions, in human health, in a decrease of ecosystem quality, and so on and so on. So we need holistic tools to identify potential of burden shift. So moving back from tools to our targets, as you know, Switzerland ratified the Paris Protocol, meaning that Switzerland engaged in a long-term net zero strategy. And you can see those are basically what does it mean in terms of political actions. And this is a text taken directly from the Federal Council that developed a long report, and today all the regulations move along those lines of rendering Switzerland net zero at the time horizon 2050. That means achieving equilibrium between sources of emissions and removals. That means addressing all sectors, not only energy, building, so on, but also including agriculture, including waste and indirect land use change, and so on. Of course, this strategy mainly covers emission directly emitted in Switzerland within the national borders, without specifically looking what's going outside. Although there is not clear objective of reducing indirect emissions from what we import as goods and services, there is also some intentions aiming to reduce this footprint due to our consumption habits. And finally, this net zero Swiss energy systems in 2050 should represent a goal that aligns ultimately all activities, economic activities within Switzerland. And to do so, Switzerland developed also a strategy And we can see that to reduce those greenhouse gas emissions towards 2050. So today we are in 2020, we can see the relative contributions of the different sectors. So buildings in green, in dark blue, we have industry, transportations in yellow, and agriculture, which is hardly to abate emissions in violet. And then we have the international aviation, which should be included also in these long-term objectives, which will still represent quite a big chunk of the overall emissions. And so we see that in 2050, according to this zero basis scenario from the energy perspective 2050, generated by the federal councils, we should be able to cut current emissions from by 4/5, but not to zero. It means that at that stage, we need to introduce negative emissions. So what does it mean? So we need to introduce carbon capture and sequestrations technologies or negative emission technologies that allows basically to take back from the atmosphere the residual emissions in order to have this Swiss strategy achieving this net zero target. And so this is what is planned on paper. Hopefully our politicians will follow up. But we need to be realistic, and this zero basis of environmental perspective 2050 scenario is not the sole one, and maybe it's not the only feasible pathways to reach that net zero targets, because we need to consider that, well, we are in an evolving policy framework. You remember, after Fukushima, we decided to phase out nuclear. And now we almost rediscussing these decisions. We are facing quite some social acceptance of of increasing, for instance, the hydro capacity to install additional wind farms. And then we have some physical constraints on the availability of hydro. So even if we have social acceptance of hydro, we cannot build more dams as the hydro potential that we have in our country. And for biomass, we have the same issues. So for instance, we cannot harvest more biomass than what the ecosystem can deliver to our society. And if we think of shifting from fossil to renewable technologies, well, we also need to ensure resilience of the whole systems. And we could also ask ourselves, what if a new disruptive technology will enter in the energy mix? So what's the penetration of this technology? So how do we evaluate the benefits or the burdens of this penetration? And so you can see we are moving on a complex and systemic, and we need a systemic perspective to address to address this really complex and sophisticated system. So, and the equation is not simple, but it is possible. So we need to satisfy our needs, the needs of our population. So in terms of mobility, in terms of energy services, I would say, making sure that we are using the available resources, and we can operate good synergies between industry, between the cities, between the food production systems, between our needs of mobility and the availability of resources, and ultimately also to sequester the residual emission that we still will have, as we've seen in 2050. And to do so, we have we have some models that you will learn to use during this MAS. Energy scope is one of those models called energy system modelings that basically relates the demands of the energy services from the society. So in terms of housing, in terms of mobility, in terms of industrial need and so on, that relates those demands with the available resources. Well, today we have fossil, but in the future, if we want to phase out of fossil, we need to rely on renewable energies. And how we can rely to those renewable resources by a set of existing conversions and storage technologies. And those models could balance these equations, fulfilling the demand with available resources with a mix of a given number of resources. And that gives an unlimited, a number of solutions that we as decision makers could select and try, depending on different constraints, technical constraints, social acceptance constraints, economic constraints, and so on and so on. And just to give you a flavor of that model, if you have some questions, feel free to ask in the Q&A sessions. We have Jonas Schnidrik, which is a PhD student at the EPFL and HSSO that exactly work on developing such a model that links national and regional capabilities to provide you typical solutions, as this one, as you can see. This is our current system of today in 2022, which strongly rely on imports of on gas, uranium, electricity, and so on. And in 2050, we need to get rid of these imports of energy and rely on our own energy that we produce with our own renewable domestic energy supply. And this is just one of the possible solutions that we might introduce and we might think using such type of models. And of course, we could also give a cost of those solutions, and moving from current systems, we can see that the most of the costs are in the operation phase. We will move on a future system that might take different forms, that basically see a reduction in cost, but also a shift from operational cost to cost into the infrastructure. So we need to be conscious that what we say, the renewable energy system costs a lot. It's more an investment in an infrastructure that will have a small operational cost in comparison of today's energy system, which has a lot of operational costs and a relatively moderate investment costs in the infrastructure. So all this to say that such energy system models again provides a technological view of how we could solve the problem, but the modern energy expert and energy planner needs to be equipped to face tomorrow's energy challenges. So he needs to understand, or she needs to understand, what are the constraints, or what are the barriers and the levers that can, on one hand, limit or encourage the deployment of new solutions. And I'm not speaking about technologies, I'm speaking about solutions, because some of those solutions might be pure technological, but some of those solutions might also be organizational or political. And so the modern energy expert, the one we would like to train, it's an expert that understands physical and technological challenges, but also social constraints and about acceptance, about ideological hostilities, that understand about economy, and that understand the political situation where we are. So which are the market regulations, which are the rights of appeal on new infrastructures, which are the economic incentives that are available to invest in novel technologies. So in addition to that, as you've seen before, these experts also need to be familiar with tools as life cycle assessments, energy system modelings. They need to understand and how to analyze public opinions, how to evaluate corporate strategies, and so on. And to do so, our solution or our goal is to propose you within this MIS a certificate or a diploma of advanced studies in sustainable energy system engineering with a specific module focused on this systemic view, system modeling. And this is headed by my colleague Michael Acklin at EPFL and myself at HSSO. And in this module, we will focus, as you have sensed, our teaching on the systemic and integrated dimensions of energy systems. Will address aspects of economic viability, social acceptability, and environmental impacts, including this life cycle perspective. Also not excluding the important question about policy, about acceptance, about resilience of the systems. And finally, also, we want also to our participants to understand, to have an idea about how energy market works, which is the political framework where we are acting, and regulatory framework that possibly limits or encourage the implementation of given solutions. And typically we'll teach courses like energy and sustainability, life cycle assessment, energy system modeling, economic principles and energy markets, resilience on energy planning and transitions, and then, of course, environmental social impact assessment, social acceptance of current and future technologies, and all this climate and regulatory framework. And of course, we cannot discuss energy without discussing about materials and about circular economy, because the more we circulate carbon, the more we circulate materials, the less we need, and the more sober we are, and the more efficient we are. And I think that I could stop here. I think it's a good transition between myself and my colleague Jean-Marie. He could take over and provide you more information about this